The fourth and final presentation in Unit 8. It's entitled Say What? 'Tis life's but a walking shadow, a poor player that struts and frets his hour upon the stage and then is heard no more. It is a tale told by an idiot, full of sound and fury, but signifying nothing. A great quote by Macbeth, William Shakespeare. The learning goals for this particular unit are that you define the properties of a sound wave and that you demonstrate the application of sound waves in everyday life. We're also going to apply all of our previously learned knowledge from this unit specifically to sound waves. So, what we already know. We already know that waves are traveling energy whose behavior can be defined. Now, we've defined waves in terms of period, wavelength, amplitude, all these sorts of things, frequency, and we know that waves will reflect, refract, and diffract at a boundary. So those are things we know. Now, what we learned in the lab is that sound frequencies can be determined by pitch. So the higher the pitch, the higher the frequency. We also determined that the amplitude can be determined qualitatively by the loudness. The louder a sound is, the greater the amplitude of that particular sound. We also learned that humans have different ranges of hearing. Some humans can hear very, very high pitches, up to 20,000 hertz. No higher, but up to 20,000. Some humans can hear very, very, very low frequencies, down to 20 hertz. We also learned that this range narrows with age, so younger people can tend to hear higher on the spectrum than many adults. So sound waves can interfere constructively and destructively. So they can interfere and make a sound louder, they can interfere and make a sound lower. Okay, sound waves. Sound is a longitudinal or compression wave. We've already talked about this quite a bit. It carries energy that is felt as vibrations. We also know that humans have a range of hearing from 20 to 20,000 hertz. Our eardrum actually converts a sound into an electrical signal for our brain to interpret. Sounds that are below 20 hertz are called infrasonic. The term infra means below. Okay, that's going to be important when we talk about the next unit. We talk about infrared. Infrared is going to mean below red. We also have ultrasonic. Ultra means above, so when we say ultrasonic, we mean above what humans can hear, or above 20,000. That's also going to come in when we talk about light, when we talk about ultraviolet light, so it's going to be light that's above violet. The frequency of sound can be described qualitatively in terms of pitch. Sounds with a higher frequency have a higher pitch. So if you were to look here, this would have a high pitch. You think of one of the notes to the far right on a keyboard. This is going to be a lower pitch, so it's going to be one of the far left keys on the keyboard. So you're going to have different frequencies give different pitches. We also know that waves travel faster the closer molecules are together. So the closer the molecules are, the faster they will travel. As a result of that, we can say that the speed of sound in air is relatively slow. The speed of sound in air is about 3.5 football fields per second, or about 343 meters per second. Now this doesn't seem like it's very slow, it seems like it's really fast. But this is why whenever people are trained runners, they're taught to look for the smoke of the starter pistol, not to listen for the crack of the gun. Okay, you don't want to listen for the crack of the gun because it actually takes a little bit of time. You will see the smoke from the gun before you will hear the crack of the gun, depending on how close you are to the starter pistol. Next, the speed of sound in water is 1483. So these molecules are a lot closer together, so we have a faster speed of sound. And then finally, we have the speed of sound in steel is 4512, which is even faster. An interesting kind of side note is you can actually do this with a friend if you're by a railroad track. You can actually take one, hit it with a hammer, and your friend will be able to hear the sound twice. Once as it travels through the rail, and once as it travels through the air. Okay, so in the movie Star Wars, the Death Star suddenly explodes in space. Explain why you can see but not hear the explosion. Well, in the movie you can actually hear the explosion, but you shouldn't be able to hear the explosion, and the reason why is sound requires matter. Okay, so you need something to carry the sound. So sound requires matter. You need something to carry the sound. In space, there's a vacuum. Since there's a vacuum, there's no matter to carry the sound, nothing can carry the sound, it shouldn't travel. The next one says gold has a density of 19.3 grams per centimeter cubed, while silver has a density of 10.5. Which would you expect to have the greater speed of sound? Based on the fact that the waves travel faster through things when the molecules are close together, you would expect the density of gold being higher to have a higher speed of sound. The next one says, what is the wavelength of middle C that is defined as having a frequency of 261.62 hertz when traveling in air? So the first thing you need to realize is this requires knowledge from the previous unit. I need to know that this is a frequency. I also need to know that I'm trying to solve for the wavelength, and the relationship that I have between wavelength and frequency involves velocity. I can use the equation v equals lambda f. When I use this, I need to figure out what the velocity is, and it doesn't state it, but it does say that it's traveling in air. So I know that the velocity is 343 meters per second. I also know that the frequency is 261.626, and I can plug into the equation v equals lambda f. I would get 343 equals lambda times 261.626. You would divide both sides by 261.626, and when you do that, you would end up with a wavelength of approximately 1.3 meters. It says a man presses his ear to a steel door that is 2 meters thick. The time that it takes for the sound to travel to his ear is 0.0058 seconds total. So, how far are the people conversing on the other side of the wall? So basically you have people conversing, and then you have a wall, and then you have somebody with their ear pressed to the wall. You want to know what the distance is between them and the wall. Well, the sound has to travel through the air, to the wall, and then through the wall. So this represents the total time that takes. The total time, we're going to call it T total, is going to equal to the time in the air plus the time in the steel. So if we could find these two times, since we have the total time, if we could find the time in the steel, that will allow us to figure out what the time in the air is, and then the distance. So the first thing that I need to do is I need to say, okay, if I can find the time in the steel, well, the distance of the steel is 2 meters. The velocity of the steel is 4512. Using the very first equation that we learned in this class, v equals v equals d over t, we can actually solve for the time in the steel. Whenever we do that, we can actually set it up as an expression that we can substitute in. Remember that we have our expression T total equals T air plus Ts. We have our total time as 0.0058 equals the time in the air plus the time in the steel. I can rearrange this equation to be T equals d over v. When I do that, I can substitute in 2 divided by 4512. Now it's just a matter of solving for the time in air. Once you have the time in air, now you have to look at it from the perspective of, once I have that time, I need to use the same equation, but I need to use it now for the air. So I take my time in air, which I just calculated, I plug it in, I have the velocity of air being 343, and I can solve for the distance. If you do everything right, you should realize that the distance in air, which is the distance between the person and the wall, is about 1.84 meters. Now, whenever something's traveling faster than sound, we have a special scale that we use, and that's called the Mach scale. Mach means the speed of sound times whatever number comes next. So when you have Mach 1, it's the speed of sound times 1, or the same value. When you have Mach 2, it's the speed of sound times 2, or 686. Here you see an example of a plane actually breaking what's called the sound barrier. Remember, sound is a longitudinal wave where it's got pressure associated with it. So as this plane breaks the sound barrier, you can actually see this cone, this cone of longitudinal waves that it's actually passing through. Okay, conditions have to be just right for this to occur. It's got to have the right humidity, the right temperature. It's an instantaneous photo. It's a great photo, though. The next one says an F-22 launches from its base 1,200 kilometers away from enemy territory. If the plane has a cruising speed of Mach 1.5, how long can the pilot relax before the mission? So the first thing you need to do is realize that's a distance, but it's in kilometers. So I need to go ahead and say it's going to be 1,200. And we need to add 3 zeros to it to make it meters. So it ends up being 1.2 million meters. Once you're there, you can say the velocity is going to be Mach 1.5, which is 1.5 times the speed of sound, which is 343. When you do this, you end up getting a velocity of the plane of 514.5 meters per second. We're going to go ahead and switch colors. You are trying to solve for the time that the pilot has to relax. The equation that you can use is v equals d over t, which is once again the first equation we learned in this class. Or you can say 514.5 equals the distance, which is 1,200,000 meters, divided by t. Multiply both sides by t, divide both sides by 514 to rearrange, and whenever you do this correctly, if you do it algebraically correctly, you should get about 2,332 seconds, which is about 40 minutes or so. So we have sonar and echolocation. Now, whenever you use sonar or echolocation, the sound is emitted and then reflected. And what we're looking for is the time differential and the fact that we know how fast sound waves travel in water. If we know how fast sound waves travel in water, and we know the time that it takes because we can measure that, we can now calculate the distance. That's what computers that run sonar actually do, and they do it very, very, very quickly. So here's an example. It says a submarine sends out a sonar pulse, receiving a ping 14 seconds later. 5 minutes later, the submarine sends out a second pulse, receiving it 13 seconds later. What is the velocity of the target if the speed of sound in water is 1.5 kilometers per second? So the first thing we want to do is we want to realize that we don't work in those units. We have to convert that to a velocity of 1,500 meters per second. Okay, some of you may be saying, well, it's 1483 in water. Well, seawater is a little bit different because it has salt in it. So we're going to go ahead and say it's 1500. The first thing is I have a signal 14 seconds later. But remember that 14 seconds is the time that it takes to receive the signal back. So if I emit a signal here, it hits something and then travels back, only half of the time is it traveling here, and the other half of the time it's traveling back. So this 14 seconds actually has to be cut in half to 7 seconds. So now we have the 1500 meters per second. We have the 7 seconds. We can calculate the distance that it is using v equals d over t. We plug in our value. We get 1500, not 15,000, equals d over 7. Whenever we take those things and multiply them out, we're going to get our value for the first ping. Okay, we're going to get the distance the submarine is originally at. But if we're trying to figure out how fast the submarine is going, we also need to figure out the second distance. So we have 13 seconds later. So I need to do the exact same calculation, 1500 equals d over, but instead of it being 7 seconds, it's going to be 6.5. When you take these two distances and you subtract them, that represents how far the submarine has traveled. Now if you have the time, which is 5 minutes, you can now figure out the velocity of this submarine. So not only is it good for figuring out exactly how far a submarine is away, but you can also figure out how fast it's moving based on the time differential for different pings. So this ends up being 300 seconds because 5 minutes is 300 seconds. And if you do the math right, you should get something along the order of 2.5 meters per second. So now, sound intensity or loudness is the measure of a loudness, which is the amplitude of a wave. So which one of these waves will be the loudest? If you look, it's the one with the largest amplitude, and that's this one. This one will be the loudest, and this one will be the quietest. Next, it says superposition and interference. Remember that since waves occupy the same space, because they are energy and not matter, they will interfere. Constructive interference results in a larger amplitude. Destructive interference results in a smaller amplitude. But most of the time, waves don't overlap perfectly. Instead, you have destructive interference here and constructive interference here. As a result, we produce something that's called a beat. Now, a beat is what you hear whenever people are trying to tune their instruments. And whenever they're trying to tune their instruments, sometimes the conductor will listen and they'll hear like a warble sound, or it gets louder and quieter and louder and quieter, and that's the process that we know as beats. Okay, you have constructive interference followed by destructive interference. Now, every time there's a beat, you can calculate what's called the beat frequency relatively easily. The beat frequency is you just subtract the frequency of the two waves. So if I have the first wave and the second wave, all I have to do is subtract those two, and that tells me what the beat frequency is. So I can tell how close instruments are being in tune. If you have one beat every second, what that means is that these are very, very close, like 256 and 255. So those instruments are very, very close to being in tune, and we can fix that relatively easily. So we have an example here. It says a student is late for a concert and does not warm up with his classmates. During the concert, while playing a high F, the student notes a beat frequency of 3 hertz. What is the frequency of the student's flute when playing a high F? Now, there's actually two options here. So if this right here is the first frequency, I can say 2793.83 minus some number has to equal 3. Or I can say some number minus 2793.83 has to equal 3. They're basically the same numbers. You end up getting something like 2790.83 or 2796.83. Those are the two options that will produce a beat frequency of 3. Resonance. Resonance is forced vibrations that match the natural vibration frequency. So if you have a wave, everything naturally vibrates, okay? If you hit something that naturally vibrates at the same frequency, it will produce a larger wave. You have constructive interference. Resonance is considered to be runaway constructive interference to the point where you can actually cause something to shatter. An example of this would be something like a wine glass. If you have a singer who's singing and there's a wine glass and their voice actually causes the crystal glass to shatter, the reason why is the frequency matches the frequency of vibration for the glass. When those two things line up, the crystal glass will shake more and more and more to the point where it shatters. This one says a tuning fork is marked with a frequency of 748 hertz. What frequency should the speaker play to cause the tuning fork to begin to vibrate? So remember, in order for resonance to occur, you can actually cause this tuning fork to start to vibrate if you play something that is exactly the same frequency. So if this thing vibrates at 748 hertz and you hit it at exactly 748 hertz, now it will begin to vibrate more and more and more. It will become louder. The Doppler effect is the apparent change in frequency due to the motion of the source or the observer. So it's the reason why an ambulance sounds different when it comes towards you as opposed to when it comes away from you. Whenever it moves away from you, the sound waves are getting further and further spread out because the source is moving as it emits the waves. Because of that, there's a greater distance between each wave or a different frequency. Since it's a different frequency, it appears to have a lower pitch. That's the reason why you can tell whether or not a train's coming towards you or away from you when you're stopped at a railroad crossing. As it comes towards you, it sounds higher, and when it goes away from you, it sounds lower. So you hear a train whistle. The pitch is lower than normal and decreasing. Additionally, the amplitude of the sound is decreasing. What can you conclude about the train? Since the amplitude is decreasing, you know it's moving away from you. And since the pitch is lower than normal, we know it's moving away, and it's decreasing. If the train was moving at a constant velocity, you would have a constant lower than normal pitch. Since it's decreasing as it's moving away from you, you can say that it's accelerating away. Okay, there are lots of medical applications for sound. We have things that are called sonic weapons that are used now because sound carries a force. You can actually use a sound blast to actually cause a physical injury. You can use ultrasonic waves to produce images of a fetus while it's still in the womb. And one of the interesting things is you can actually use sound waves to break up kidney stones while they're still in the body so that you don't have trouble passing them. That way it avoids some of the pain associated with kidney stones and can actually prevent the need for surgery.